The suspension system plays three important roles within a vehicle. It supports the weight of the vehicle, it provides a layer of separation between the vehicle and the road, and it keeps the wheels touching the ground. The suspension accomplishes these three tasks via a spring-obeying Hooke's law. Hooke's law states that the force generated by a spring is equal to its displacement multiplied by its negative stiffness. The displacement is the difference in length between the spring's resting length and the spring's current length, and the stiffness can be thought of as the strength of the spring, or how hard it resists displacement. What this means is that given a negative displacement, i.e. the spring is in compression, a positive restoring force is generated, pushing the spring back to its original shape. When the displacement is positive, i.e. the spring is in tension, the exact opposite happens. Within a real-time application, we model a suspension spring by checking the distance between the spring's start position, which we call the top link, and the ground immediately beneath it, subtracting the wheel's radius before recording the length. From this, we can compare the value to the spring's resting length, a value we defined beforehand to get the spring's current displacement. We can then multiply this value by the spring's stiffness to get the force the spring is generating. This is what the code looks like. Back in Unity, we will first create an empty and name it top links, and from it we will give it 4 children, positioning them where we want our suspension to attach to the vehicle chassis. Next, we'll create another empty named colliders and give it a child with the vehicle's mesh collider attached to it. After that, we'll create a new collision layer, naming it vehicle colliders, and set the collider empty to have this layer. Then we'll attach our wheel script to each one of the 4 top links and configure them appropriately. Here are some values I ended up using. Feel free to tune according to your needs. Finally, attach a rigid body to the vehicle object, set its mass appropriately, and hit play. It's a promising start, but one obvious issue we have is that our vehicle keeps bouncing and never reaches a steady state. This is because we still haven't implemented damping. Along with the spring, a vehicle's suspension also contains a shock absorber. The shock absorber's job is to dampen the oscillations of the spring motion so that the suspension can reach a steady state. A vehicle's shock absorbers are governed by the damping equation, which states that the damping force generated is equal to the velocity of the spring, which is simply how fast the spring's displacement is changing, multiplied by the damping stiffness. As you can see, higher stiffness values bring the suspension to a steady state quicker up until a certain point. When this point is reached, the spring is said to be critically damped. Adding damping to our suspension simulation involves adding the following lines of code. Back in our scene, let's set an appropriate damping stiffness for our vehicle and hit play once again. That solved our issue, and with that we can move on to having our wheel meshes update with the suspension. Create a new script and name it Visuals and open it up. We're going to need to reference our wheel script for this. In the late update function, we want to set our wheel mesh's local position to be equal to our top link's local position minus the suspension's current length. Save the script and attach it to our 4 wheel meshes, making sure to attach the corresponding top link to each one. Looks like it's working. With this, we're also now able to play around with our suspension values a bit more and better see how they affect our vehicle's ride.